The mantis shrimp's dactyl club doesn't just strike its prey, it accelerates so violently it rips the very fabric of the water itself, generating superheated cavitation bubbles hotter than the sun's surface, a localized vacuum that defies everything we thought possible in a liquid medium. This isn't just a punch, it's a controlled, microscopic explosion occurring hundreds of times per second, a weaponized re-engineering of fundamental physics. You are about to discover the hidden mechanics behind a creature that weaponizes a phenomenon human engineers have spent decades trying to control, the implosive power of a void. We will dissect the specialized materials and biomechanical marvels that allow this tiny crustacean to repeatedly unleash a force that, by all conventional understanding, should tear its own limbs apart. This astonishing ability, found across hundreds of species of mantis shrimp, centers on the intricate interplay between its club-like appendage and the water surrounding it. When the mantis shrimp decides to hunt, it doesn't just swing its club. It loads a microscopic spring latch system, an internal architecture that snaps shut with incredible force. The club, a structure often no larger than a human fingernail, then accelerates from 0 to over 30 meters per second in less than 0.003 of a second. To put that into perspective, you are looking at an acceleration that outstrips a .22 caliber bullet by a factor of over 2,000. The speed is so extreme, the pressure exerted by the club as it moves through water drops precipitously in its wake. This sudden, massive drop in localized pressure forces the water to instantaneously vaporize, forming a temporary, empty void, the cavitation bubble. Imagine, if you will, the snap of a bullwhip, but instead of air, it cracks through an impossible liquid space. This isn't just a tiny vacuum, it's a dynamic, volatile entity. Once formed, these bubbles are inherently unstable. The surrounding water, under immense pressure, rushes back in to fill the void, collapsing it with incredible violence. This implosion generates two distinct weaponized effects. First, an intense shockwave radiates outwards, capable of stunning, dismembering, or outright killing prey from a distance without direct contact. Secondly, as the bubble collapses, it creates localized temperatures that spike to several thousand Kelvin, briefly exceeding the surface temperature of our sun, alongside pressures reaching thousands of atmospheres. For a fraction of a millisecond, a microscopic furnace ignites underwater, fueled by the very water it displaces. Dr. Sheila Paddock and her colleagues at Duke University, in their landmark 2005 paper, meticulously detailed the kinetics and morphology of these strikes, revealing the mechanical advantage provided by the saddle and latch structures that enable such extreme accelerations, fundamentally redefining how we understood muscular power output in the animal kingdom. What truly elevates this mechanism from mere biological curiosity to a profound engineering marvel is not just the generation of these extreme forces, but the creature's ability to repeatedly survive them. Our own attempts to harness or control cavitation, whether for cleaning processes or even advanced propulsion, are often limited by the destructive potential of the imploding bubbles. The forces involved are immense, capable of eroding steel and pitting propeller blades over time. Yet a mantis shrimp, often smaller than your hand, can deliver thousands of these microexplosions throughout its lifetime without its dactyl club disintegrating. How? The answer lies within the club's extraordinary material science, a masterpiece of biological engineering. Scientists like James Weaver and David Casalis have meticulously mapped the club's layered architecture. It's not a single homogeneous material, but a complex, hierarchical composite, predominantly composed of chitin fibers and protein. In a critical study published by Rivera and colleagues in 2018, focusing on the highly refined structure of the impact region, it was revealed that these fibers are arranged in a helicoidal or twisted plywood pattern. Each layer of fibers is rotated at a slight angle relative to the one beneath it, forming a spiral structure. This precise arrangement acts like a microscopic spring and shock absorber system, allowing the club to dissipate the massive energy from both the initial strike and the subsequent cavitation bubble implosion. When the immense force impacts the club, the energy isn't absorbed uniformly or reflected destructively. Instead, it's dispersed across multiple planes, twisting and deforming the layered structure in a controlled manner, preventing catastrophic failure. Think of it less like a solid hammer and more like a perfectly engineered multi-laminate composite designed to deform just enough to spread the load without breaking. Our best military-grade ceramics and advanced composites aim for similar energy dissipation, but a mantis shrimp achieves this with organic materials repeatedly in a hyper-aggressive environment. Could our navies learn from a crustacean? This isn't just about a shrimp, it's about breaking fundamental material limits. This astonishing biological innovation extends far beyond a single species, revealing deeper truths about evolutionary pressures and the relentless pursuit of survival. The mantis shrimp's strategy illustrates a common evolutionary theme: the refinement of specialized tools to dominate a specific ecological niche. One fascinating extension of this principle is the divergence in mantis shrimp morphology itself. There are broadly two types: the smashers, like our primary subject, with their robust, club-like appendages, and the spearers, which possess barbed, spear-like forelimbs. While both rely on incredibly fast strikes, their application differs. Spearers use speed to impale soft-bodied prey like fish, often with their raptorial appendages acting as an underwater projectile, generating smaller but still significant cavitation bubbles as a secondary stunning effect. Smashers, conversely, prioritize the cavitation bubble's full destructive potential, aiming their blunt clubs at hard-shelled mollusks and crabs, effectively turning water into a localized grenade. Both have independently engineered ways to leverage hydrodynamic forces for predation, but their adaptations manifest in distinct physical forms. Furthermore, this extreme biomechanics drives a fascinating sensory arms race. How do prey species detect or evade such a rapid, devastating strike? Some fish, for instance, have evolved highly sensitive lateral line systems that can detect the subtle pressure changes and acoustic signatures preceding or accompanying a cavitation event, giving them a fraction of a second to react. Conversely, some mantis shrimp species have refined their striking mechanics to minimize these telltale signs, ensuring a silent, invisible kill, further illustrating the intricate evolutionary dialogue playing out in the reefs. Finally, the mantis shrimp's club is now a profound inspiration for human engineering, giving rise to an entirely new field of biomimetics. Researchers are actively studying its helicoidal structure to design tougher, lighter composite materials for applications ranging from aerospace components and car frames to body armor and sporting equipment. The lessons learned from this tiny creature could lead to breakthroughs in impact-resistant materials that dissipate energy more effectively than anything currently available, potentially revolutionizing everything from how we build safer vehicles to how we protect soldiers. It's a testament to nature's unmatched R&D department. You will never look at the ocean floor, or indeed any natural habitat, in quite the same way. What once seemed like a serene, colorful landscape is now revealed as a dynamic laboratory, a high-stakes proving ground where evolution relentlessly engineers solutions that often surpass our most advanced human technologies. Every creature, every structure, every seemingly simple interaction holds a blueprint for an astonishing biological mechanism, a hidden design principle, a radical re-engineering of the laws we thought were absolute. The mantis shrimp isn't just an anomaly, it's a testament to the radical solutions evolution can forge when faced with ecological pressures. The living world is full of such re-engineered realities, waiting for us to uncover their blueprints. What other foundational laws do we think are absolute, only to find they've been creatively circumvented right under our noses?